What if you could create and control a single particle of light whenever you wanted? Welcome to Summarize Science. Today, we're looking at new research where a team has built a tiny, tunable device to do just that. These devices, called single-photon sources, are essential building blocks for things like unhackable quantum communication and incredibly powerful quantum computers. The team started with an amazingly thin material called tungsten disulfide, or WS2, which is just a few atoms thick. They zapped this material with hydrogen ions, which cleverly created microscopic domes, or bubbles on its surface. These domes act like perfect little traps for energy, which can then be released as a single particle of light, or a photon. But just creating a single photon isn't enough. You also need to control it and catch it efficiently. To solve this, the researchers built what's called an open cavity. You can think of it as a microscopic echo chamber for light. It's made of two highly reflective mirrors placed incredibly close together, with a special WS2 material sandwiched right in the middle, as you can see in this diagram. This cavity is designed to trap the photon, bouncing it back and forth to amplify its signal and make it much easier to work with. This image shows an actual microscope view of the material, with the domes appearing as tiny bright spots where the photons are born. What's truly amazing about this setup is that it's tunable. By precisely changing the distance between the two mirrors, the researchers can perfectly match the cavity to the specific color, or energy, of the photon being emitted. This graph shows that tuning in action. As they change the mirror distance, you can see the bright signal from the cavity sweeping across the photon's natural emission line. When they hit that perfect resonance, the brightness of the light source is enhanced by a factor of 17. But how can they be absolutely sure it's only one photon at a time? They use a special measurement, shown in this graph, that proves the quantumness of their light source. If you were using a regular light bulb, photons would arrive randomly, but for a true single photon source, you should never detect two photons at the exact same instant. That big dip right at the center confirms it. The device is releasing photons one by one. The researchers also found that the photon's emission is affected by tiny vibrations in the material, which are known as phonons. These vibrations can interact with the photon, which has a significant effect on how the light source behaves inside the cavity. Understanding this interaction is key to optimizing the performance of these quantum devices. So, let's quickly recap what makes this so important. The researchers created single-photon emitters in an atomically thin material by forming nanoscale domes. They then placed this inside a tunable, echo chamber for light, which allowed them to significantly boost the signal's brightness. Most importantly, they proved it was a true quantum source, releasing light one particle at a time. This work is a big step forward because these microdomes can be created in specific, predetermined locations, making them much easier to build into larger, more complex quantum circuits. Developing controllable and scalable single-photon sources like this is absolutely crucial for building the next generation of quantum technologies. Thanks for watching Summarize Science.